The generational leap from the standard definition era of the PlayStation 2 to the high-definition landscape of the 7th generation of video game consoles presented the interactive entertainment industry with an unprecedented software engineering crisis. At the forefront of this technological disruption was Rockstar Games, a studio determined to redefine the open-world genre with the development of Grand Theft Auto 4. Moving away from the licensed renderware engine that had powered the three-dimensional trilogy of the previous era, Rockstar constructed the Rockstar Advanced Game Engine, a proprietary framework engineered to handle cutting-edge physics, sophisticated artificial intelligence routines, and high-fidelity asset streaming. Liberty City was envisioned as a seamless living metropolis completely devoid of traditional loading screens, requiring the game engine to dynamically page highly detailed geometry, high-resolution texture maps, and complex audio files into memory as the player traversed the environment at high speeds. However, as the development pipeline shifted towards concrete hardware implementation, Rockstar's visionary engineering collided directly with the exotic, highly non-standard internal architecture of Sony's PlayStation 3, igniting an internal technical crisis that brought the multi-million-dollar project to the absolute brink of cancellation. The core of this systemic friction traced back to a fundamental architectural divergence between the two dominant hardware platforms of the era, the Xbox 360 and the PlayStation 3. Under the direction of Ken Kutaragi, Sony engineered the PlayStation 3 not as a traditional consumer gaming console, but as an ambitious cell-powered computing node designed to dominate the broader consumer electronics market through sheer, unorthodox processing power. This philosophical approach completely blindsided traditional software developers who had spent decades mastering linear, single-threaded programming environments. While Microsoft equipped the Xbox 360 with a highly flexible, unified memory architecture consisting of 512 megabytes of GDDR3 RAM that could be dynamically allocated between system logic, geometry, and textures based on the immediate needs of the software, Sony implemented a rigidly segmented, unyielding memory topology. The PlayStation 3 split its 512 megabytes of total memory into two completely isolated 256 megabyte pools. 256 megabytes of high-speed XDR system memory dedicated exclusively to the central processing unit, and 256 megabytes of GDDR3 video memory allocated strictly to the reality synthesizer graphics processing unit. This split memory architecture proved to be an absolute choke point for the Rockstar Advanced Game Engine's asset streaming pipeline, which had been organically designed around the assumption of a unified memory pool. In an open-world environment where a player could hijack a high-performance sports car and accelerate through a densely populated urban intersection, the game engine needed to simultaneously stream in building meshes, vehicle physics models, pedestrian artificial intelligence logic, and high-fidelity audio streams.
On the Xbox 360, the engine could dynamically borrow unused video memory to buffer system logic or allocate excess system RAM to temporarily hold high-resolution textures. On the PlayStation 3, this fluid reallocation was mathematically impossible due to a hardware barrier. If the system memory pool hit its hard 256 megabyte ceiling, the engine would suffer immediate catastrophic memory leaks, resulting in hard software crashes within mere minutes of booting early development builds. To prevent these fatal exceptions, engineers were forced to throttle the asset pipeline, which caused severe immersion-breaking asset pop-in, where entire skyscrapers, roads and vehicles would materialise out of thin air seconds after the player had already arrived at the location. The compounding technical instability of the PlayStation 3 build created an intense internal crisis within Rockstar Games, pushing executive leadership to seriously evaluate the financial and operational viability of abandoning the Sony platform entirely. The game was lagging months behind its projected milestone schedule, and the intense engineering bottleneck was draining critical labour resources away from the primary development pipeline. This organisational friction was further magnified by intense macroeconomic pressures, as Microsoft had secured a high-profile $50 million exclusivity agreement for Grand Theft Auto 4's subsequent episodic downloadable content, placing immense structural pressure on Rockstar to deliver a flawless, synchronous multi-platform launch. Early internal reports indicated that to make the game boot reliably on the PlayStation 3 without crashing, the visual fidelity would have to be downgraded so severely that it would risk permanently damaging the brand equity of the franchise and creating a catastrophic market imbalance between the two versions. The development team was hitting an unyielding wall of corporate bureaucracy and hardware limitation, realising that traditional optimisation methods were completely incapable of salvaging the project. The ultimate salvation of the PlayStation 3 version required a radical ground-up conceptual pivot in how Rockstar's engineers approached the underlying architecture of Sony's Cell broadband engine. The Cell processor was a Frankensteinian silicon construct composed of a single PowerPC-based power processing element paired with 8 co-processing units known as synergistic processing elements, 7 of which were active in retail hardware units. The central power processing element was notoriously weak when handling traditional linear execution threads due to its in-order execution pipeline and high latency penalties. Traditional programming frameworks that attempted to dump the entire game logic onto the main processor quickly caused severe CPU bottlenecks, leaving the 7 auxiliary synergistic processing elements completely underutilized.
Rockstar's software engineers realised that to save the project, they had to stop treating the PlayStation 3 like a standard centralised gaming console and begin treating it like an asynchronous distributed parallel supercomputer, manually restructuring the engine's entire task scheduler to offload computational weight away from the main processor. This engineering pivot forced Rockstar to implement a hyper-detailed low-level micromanagement pipeline that sliced the game's core algorithmic tasks into miniature data packets tailored for the synergistic processing units. This was an extraordinarily grueling manual process because each unit possessed a tiny, highly isolated local store memory of just 256 kilobytes, requiring data to be precisely broken down, packaged, and transferred via direct memory access ring buffers. Engineers painstakingly extracted complex systems, including the intensive Havoc physics calculations, the sophisticated Euphoria procedural animation engine responsible for realistic pedestrian weight and impact responses, audio decompression routines, and asset de-archiving pipelines, and mapped them directly onto the parallel coprocessors. If a data packet exceeded the 256 kilobyte limit by even a single byte, the specific unit would suffer a local memory overflow, instantly fracturing the game's physics grid or silencing the audio stream. By transforming the Cell processor into an array of micro-engines running simultaneous asynchronous tasks, Rockstar successfully bypassed the weak main processing unit, maximizing the computational throughput of the hardware to a degree that few third-party studios had ever attempted. The technical triumph over the central processor, however, did not completely solve the hardware limitations of the PlayStation 3's reality synthesizer graphics chip, which lacked the advanced unified shader architecture and superior fill rate capabilities of the Xbox 360's custom Xenos GPU. To compensate for this graphics bottleneck, Rockstar's engineers executed a secondary highly unconventional maneuver, leveraging the unutilized computational overhead of the parallel processing units to act as a co-graphics processor. They wrote custom software rasterizers that allowed the co-processors to intercept raw vertex data, perform complex geometric transformations, and handle intensive post-processing visual effects before passing the completed frames back to the graphics hardware for final display rendering. This brilliant software workaround allowed the team to bypass the physical limitations of the graphics chip, but it still required sharp technical compromises to ensure a stable target frame rate of 30 frames per second. The native horizontal resolution of the PlayStation 3 version was intentionally downscaled to 1152 by 640 pixels, a distinct drop from the Xbox 360's native 1280 by 720 resolution, and a specialized hardware-accelerated anti-alias in blur filter was applied to mask the upscale, resulting in a distinctly softer, more atmospheric visual presentation that came to characterize the Sony version.
When Grand Theft Auto 4 finally launched globally in April 2008, the fact that it ran smoothly on both platforms was universally recognised by software architects as an absolute miracle of low-level optimisation and sheer engineering willpower. The grueling, painful rewrite of the Rockstar Advanced Game Engine to accommodate the PlayStation 3's fragmented memory and parallel processing architecture ultimately yielded massive long-term dividends for the studio, building a highly sophisticated institutional knowledge of multi-threaded parallel processing early in the hardware cycle. This optimization blueprint served as the foundational bedrock that empowered Rockstar to push the envelope with subsequent open-world masterpieces, including Red Dead Redemption in 2010 and LA Noire. This mastery culminated in the twilight of the 7th console generation with the release of Grand Theft Auto V in 2013, a game that managed to stream a vast, geographically diverse map with highly superior visual fidelity on the exact same limited hardware infrastructure that had choked the original builds of its predecessor 5 years earlier. The collective industry-wide struggle to program for the PlayStation 3, championed by intense developer feedback from elite studios like Rockstar, Valve and Insomniac, ultimately forced a monumental paradigm shift within Sony's internal hardware design philosophy. The executive arrogance that had birthed the exotic, developer-hostile cell architecture was completely dismantled as Sony prepared for the subsequent console generation under the technical leadership of Mark Cerny. The design mandate for the PlayStation 4 completely abandoned the complex parallel processing gimmicks of the past in favour of absolute developer friendliness, adopting a standard x86 architecture and a massive unified pool of 8GB of ultra-fast GDDR5 RAM. The agonising memory barriers and micromanaged data packets that Rockstar had to invent to make Liberty City function on the PlayStation 3 directly influenced the creation of modern, streamlined hardware environments that prioritise developer efficiency over theoretical, unmanageable processing power. Ultimately, the turbulent development history of Grand Theft Auto 4 stands as a definitive historical monument to software engineering overcoming systemic hardware friction, proving that true technical genius lies not in the perfection of the silicon, but in the adaptability of the code that commands it.